Hello, so I hope you guys are doing good. So on this video, I'm going to talk about the piecewise continuous function, and also I'll give you a definition of a function of exponential order. Okay, so fx, a function fx is called piecewise continuous function on an interval I if the interval I can be partitioned into a finite number of subinterval on which the function is continuous on each open subinterval and has a finite limit at the endpoints at endpoint of each interval. Okay, so if you look at this, for example, suppose you have like a function is defined, suppose like that. Okay, so this function is piecewise continuous function because see, I can divide this whole interval into small pieces, right, such that the function is continuous at each of these pieces. You see that? So this is a piecewise continuous function. If a function is piecewise continuous on an interval AB, then the integral exists, right? But how do I find out the integral? You find out the integral from this to this, and then plus this to this, plus this to this, plus this to this. And you add that, so that will be, the integral exists, meaning the integral will be finite. In case of the improper integral, a to infinity fx dx, if one of the limit is infinity, then this is the improper integral. In this case, just continuity is not enough for the integral to exist, right? The function should go to zero rapidly. For example, if you have a function that is like, suppose this is a and then go to infinity like that, you see that? So this is the integral a to infinity fx dx. Here it diverges, right? It does not exist. But when does it exist is, to have this type of integral exist, you must have a and then it must go to 0, right? So that in this case you have a to infinity fx dx exists in this case because the area will be finite, you can say, in other words, or the integral will be finite in this case. But in this case the integral is not finite. Okay, so let us write the definition here. A function ft is said to be of exponential order a if there exists a positive constant m and k positive also, such that absolute value of ft is less or equals to k times e to the at for all t greater or equals to m. So after the mth time, after the time point m, if the absolute value of the function ft is less or equals to k times the exponential function, okay, then we call that ft is of exponential order. In other words, a function of exponential order grows no faster than k times e to the at as t tends to infinity. For big time points, after mth time point, all the terms of the function must be less or equals to, or bounded by, you can say, bounded by k times e to the a times t for t greater or equals to m, right? When t tends to infinity, the function must be smaller than or less or equals to k times e to the at. In that case, we call that ft is a function of exponential order order a. So let's see one note. One way of checking exponential order of a function ft is to compute the limit of this ratio, absolute value of ft over e to the at, limit t tends to infinity. And if this quantity is finite, if this goes to a finite number, then we say that this is of exponential order, or otherwise it will not be of exponential order. So we will see some examples. Okay, that is the name. Okay, let us see this example. Which of the following functions are of exponential order? So the first function is ft equals to cosine bt. The second is ft equals 5t squared, and the third one is ft equals to e to the t cubed. Okay, so for the first one, what we do, as suggested in the previous slide, I just removed that. So that is what we do is we take limit t tends to infinity, right, and then you do ft absolute over and then e to the at, right? So what do you get? Limit t tends to infinity. Absolute value of that is cosine of bt, right? So, and then divide by e to the at. So when you take the limit t tends to infinity, whatever value of b is, this will be finite, right? So this will be less than 1. So but when when t tends to infinity, then this goes to infinity, right? So 1 over infinity, or some finite number over infinity, is 0 if a is positive, right? For a positive, this is exponential. This is a function of exponential order. Okay, let's do number b. Is limit t tends to infinity, f of t over e to the at, right? There is a limit t tends to infinity. What is absolute value of f of t? Is 5t squared, right? Because it is positive, so you don't need the absolute value, e to the at. So if you take the limit there, you will get infinity over infinity, right? So what you do is you need to use the L'Hopital's rule, right? So how do I use the L'Hopital's rule? Is you find out the derivative of the numerator separately and the derivative of the denominator separately. So limit t tends to infinity. What is the derivative of that? It is 10t over a e to the t. You see that? So how about here? Equals to limit t tends to infinity. Use the L'Hopital's rule again, because when you plug in the limit here, you will get infinity over infinity at there. Infinity over infinity, right? So what you get there is 10 over a square t, e to the at, right? E to the at. So a square times e to the at. Now take the limit. So for any finite value of a, right, or any infinite value of a, this will be this quantity will be very big. You see that? This quantity will be very big. So 10 over a big quantity will be 0 as well. So this is also a function of exponential order. So it is yes. This is also yes. Okay. So how about triple I or C? So let's take that limit t tends to infinity. Absolute value of f of t over e to the at is equals to limit t tends to infinity, right? E to the t cubed over e to the at. So this is infinity over infinity. If you use the L'Hopital's rule, it will never end, right? Because you will get infinity over infinity, because you will get e to the something over e to the something, like that. So what I want to do here is write limit t tends to infinity, e to the, I write t cubed minus at, right? So this can be written as limit t tends to infinity, and then you write e to the, let's take t out, you get t squared minus a. You see that? So when t tends to infinity, what happens to this? This goes to infinity, right? This basically goes to infinity because a is finite. So this goes to infinity, and so what happens is this will become infinity basically. E to the infinity is infinity, right? So it is not a function of exponential order. You see that? So let me write one theorem, because you know the Laplace transform is defined as the integral, right? The improper integral, right? So when does the improper integral exist? Is basically if the integral goes to 0 rapidly, right? Otherwise the improper integral will not be finite. So this theorem says when does the Laplace transform exist. Okay, so let's write down theorem. Theorem is, suppose f is piecewise continuous. Suppose f is piecewise continuous on an interval 0 to a. Okay, so for any positive positive number a, and f is of exponential order. If this is the case, then the Laplace transform of f f exists for s greater than a. Exist for s greater than a. So this is the existence theorem for the Laplace transform. Okay, the function f must be piecewise continuous, and f must be of the exponential order, meaning it is not blowing up. Okay, it is going down to 0. So in that case, the Laplace transform of the function f exists. Okay, so this is the end of chapter 5 section 1. So I think I assigned the homework problem already. If not, so let me write down that again. So homework problem is section 5.1, and then question number is 6, 8, 17, 23, and then 25. These are the homework problems. Okay guys, thank you.